Time is one of the most fundamental and mysterious concepts in both everyday life and scientific inquiry. Despite its omnipresence, time remains difficult to define with precision. It governs everything we do, from the smallest biological processes in our bodies to the vast movements of galaxies across the cosmos. And while we're talking about time, take a minute to subscribe and leave a like. We wake, eat, sleep, work, and live by its rhythms. Yet, when we try to answer the simple question, what is time? We quickly encounter a web of complex, sometimes contradictory ideas. It is both a measure and a medium, both continuous and discrete, both intuitive and abstract. The very fact that we experience the passage of time so naturally makes it all the more elusive to analyze. Philosophically, time has long been a subject of deep contemplation. Ancient philosophers like Heraclitus viewed time as the essence of change, a river into which one cannot step twice. Plato and Aristotle considered time in relation to motion and change, with Aristotle famously describing it as the number of movement in respect of before and after. Saint Augustine of Hippo, writing in the 4th century, articulated the paradox of time most succinctly when he said, "What then is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know." His reflections on past, present, and future, and the idea that only the present truly exists, echo through centuries of philosophical thought. In modern philosophy, Immanuel Kant proposed that time is not something that exists independently of the mind, but rather a structure imposed by the human mind to make sense of experience. According to Kant, space and time are part of the basic framework through which we perceive the world, not properties of things in themselves. Meanwhile, philosophers like Henri Bergson pushed back against the notion of time as merely a measurable, spatial quantity, emphasizing instead the flow of time as it is subjectively experienced, what he called duration. In daily life, we operate with a more pragmatic sense of time. We divide it into units, seconds, minutes, hours, days, weeks, and we plan our lives around these segments. We experience time linearly. We remember the past, experience the present, and anticipate the future. But even in these ordinary ways of thinking about time, there's an underlying assumption that time is something real, something objective that moves forward at a steady pace, carrying us along with it. This belief, however, has been challenged repeatedly by developments in science, which suggest that time is far more complex, malleable, and relative than our common sense tells us. The need to measure time precisely is not just a modern obsession. Human beings have been tracking time for thousands of years, using whatever tools were available to them. Initially, these were the cycles of the sun and moon, the changing seasons, and the patterns of the stars. Later came sundials, water clocks, and mechanical devices. Each innovation in timekeeping technology reflected not only a better understanding of nature, but also a deeper desire to control and structure human activity. The measurement of time became essential for agriculture, navigation, religious rituals, industrial production, transportation, and communication. Timekeeping moved from being a philosophical curiosity or religious duty to a practical necessity. Scientific progress has fundamentally transformed how we think about time. Newton, in the 17th century, formulated a concept of absolute time, an ever-flowing, universal parameter independent of the events it orders. For Newton, time ticked uniformly, whether or not anything was happening. This idea held sway for centuries and supported the development of classical mechanics. But in the early 20th century, Einstein upended this view with his theories of relativity, demonstrating that time is not universal at all. Instead, it is affected by speed and gravity. The faster you move, the slower your time runs compared to someone at rest. The stronger the gravitational field, the more time dilates. These insights were not just theoretical. They have been confirmed experimentally and have real-world implications, especially in technologies like GPS, which must account for relativistic effects to maintain accuracy. In parallel with relativity, quantum mechanics introduced even deeper uncertainties. At the quantum level, time behaves in ways that defy classical intuition. It lacks a well-defined operator in the fundamental equations of quantum physics, and some interpretations of quantum theory even suggest that time might emerge from more fundamental timeless states. Cosmology has further complicated the picture by exploring the origin and structure of time itself. In the context of the Big Bang, time may have had a beginning, a concept that strains our understanding and raises profound questions about causality and existence. Despite centuries of thought and observation, we still don't have a single, unified theory of time. It is one of the major unsolved problems at the intersection of physics, philosophy, and consciousness studies. Is time fundamental, or is it emergent? Is it continuous or discrete? Is the flow of time an illusion? Does the future already exist, or is it yet to be determined? And why do we perceive time as moving from past to future? This introduction sets the stage for a deeper exploration of how our conception of time has evolved in tandem with scientific development. From primitive observations of the sky to the precision of atomic clocks and the puzzles of quantum physics, science has not only refined our ability to measure time, but also fundamentally altered our understanding of what time is. As we trace the history of timekeeping and the ideas that shaped it, we'll see how each technological and theoretical leap forced humanity to rethink not just the mechanics of time, but its meaning. What started as a need to track the sun's position became a journey into the fabric of reality itself. Long before scientific instruments, equations, or theories, human beings experienced time through the natural rhythms of the world around them. The passage of time was not measured by machines but felt in the rising and setting of the sun, the changing of the seasons, the waxing and waning of the moon, and the cycles of birth, growth, decay, and death. In the pre-scientific era, time was not an abstraction but a lived reality intertwined with survival, agriculture, and spirituality. These early perceptions of time were shaped by direct observation, myth, and ritual, forming the basis of human culture and civilization. In the earliest human societies, the most immediate indicator of time was the alternation between light and darkness. The day-night cycle became a fundamental unit of time, guiding daily activities such as hunting, gathering, cooking, and resting. Similarly, the phases of the moon and the patterns of the stars provided clues to the passage of longer intervals. These observations allowed early humans to predict changes in the environment, such as tides, animal migrations, and the arrival of cold or rainy seasons. For communities dependent on agriculture, such predictions were crucial. Planting and harvesting had to be timed accurately to ensure survival. Over time, humans began to formalize these observations into early calendar systems. These systems varied from culture to culture, but often combined solar and lunar cycles. For example, ancient Mesopotamians used a lunisolar calendar that aligned months with the phases of the moon and adjusted years based on the solar cycle. In Egypt, a calendar based on the heliacal rising of the star Sirius helped predict the flooding of the Nile, a critical agricultural event. In Mesoamerica, the Mayans created an intricate calendar system that combined a 260-day ritual calendar with a 365-day solar calendar, reflecting both spiritual and agricultural concerns. Ritual and religion played a central role in shaping pre-scientific notions of time. Many ancient societies saw time as cyclical rather than linear. In these worldviews, events repeated themselves in a cosmic rhythm. Seasons returned, generations followed one another, and the same stories unfolded again and again. Hinduism, for instance, describes vast cosmic cycles called yugas, each lasting millions of years and repeating indefinitely. Similarly, the Aztecs believed in successive worlds or suns, each created and destroyed in turn. These beliefs reflected an understanding of time as a repeating cycle of creation, preservation, and destruction, a pattern evident in the natural world and projected onto the divine. In such societies, time was often considered sacred. Religious festivals and rituals were aligned with celestial events to maintain harmony between human actions and cosmic order. The solstices and equinoxes were not just astronomical phenomena, but spiritual moments, celebrated with ceremonies meant to ensure fertility, prosperity, or divine favor. Temples and monuments were frequently aligned with the sun, moon, or stars, serving both as places of worship and as tools for astronomical observation. Stonehenge in England and the Great Pyramid of Giza in Egypt are famous examples of such structures. These sites show that even without modern tools, early civilizations had a sophisticated understanding of celestial cycles and their importance to human life. Yet, this understanding was not scientific in the modern sense. Time was not thought of as an independent dimension or a quantity to be measured precisely. Rather, it was experienced as part of the natural and spiritual order, something inseparable from the land, the sky, and the gods. The past, present, and future were not always distinct categories. Oral traditions and mythologies often blurred the boundaries between them, with ancestral stories living on in the present and prophecies shaping actions yet to come. Time was relational, embedded in the environment and in human activities, not something that ticked away uniformly in the background. Nevertheless, the need to coordinate communal life gradually led to more formalized timekeeping. In early city-states and empires, the complexity of social organization demanded shared temporal structures. Agricultural schedules, trade agreements, taxation, and legal proceedings all required a common understanding of dates and durations. This led to the development of administrative calendars, often overseen by priests or astronomers. These calendars reflected not only astronomical knowledge, but also political and religious authority. The ability to predict eclipses or seasonal changes was seen as a sign of divine favor and gave rulers a powerful tool for legitimizing their control. In some cases, the tracking of time became a form of control over people. In ancient China, the emperor was seen as the mediator between heaven and earth and the regulation of time, including the declaration of calendars and the observance of festivals, was a core aspect of imperial power. Similarly, in ancient Rome, the calendar was originally controlled by the pontifices, a group of high-ranking priests who could manipulate the length of months and years for political purposes. The later reform of the Roman calendar under Julius Caesar, which introduced the Julian calendar, was both a scientific and a political act, reflecting the desire for a more rational and stable temporal framework. Despite the many differences in how ancient cultures understood and used time, certain patterns emerge. Time was almost always linked to nature, particularly the heavens. It was often cyclical, spiritual, and communal. It was marked by events, solstices, harvests, rituals, rather than by a continuous flow. There was no notion of clock time as we understand it today. Instead, time was embedded in context, interpreted through experience, and measured by observation rather than by standardized units. This pre-scientific era laid the groundwork for later developments. The careful observation of celestial bodies, the invention of calendars, and the association of time with religious and political structures all contributed to the growing human awareness of time as a dimension that could be studied and, eventually, measured. As societies became more complex, the limitations of observational and ritual-based timekeeping became apparent. The stage was set for a new kind of understanding, one based on mechanics, mathematics, and eventually, atomic precision. The shift from natural, cyclical, and sacred time to abstract, linear, and measurable time was not abrupt, but it marked a profound transformation in human thought. This transformation would begin with the development of instruments like sundials, which sought to capture the movement of the sun in physical form. These devices represented an early attempt to separate time from events, to treat it not just as a background to action, but as something that could be quantified, predicted, and standardized. It was the first step in a long journey that would ultimately lead to the scientific revolution, modern physics, and the ongoing search to understand the true nature of time. The sundial represents humanity's earliest known attempt to capture and quantify the passage of time through mechanical means. It is a remarkable intersection of observation, astronomy, geometry, and human ingenuity. More than just a tool, the sundial was a bridge between the pre-scientific perception of time, bound to nature and ritual, and the emerging idea of time as something measurable, predictable, and structured. It signaled a fundamental shift, from experiencing time through change and rhythm to observing time through angles, shadows, and calibrated surfaces. The concept behind the sundial is elegantly simple. A vertical rod or stick, known as a gnomon, casts a shadow onto a flat surface marked with hour lines. As the sun moves across the sky from east to west, the position of the shadow changes, allowing the observer to determine the approximate time of day. This principle relies on the consistent motion of the sun, or more accurately, the Earth's rotation. The sundial does not measure time in the abstract, but tracks the position of the sun relative to the horizon. In this sense, it is both a natural and a constructed timepiece, rooted in celestial mechanics, but shaped by human design. The earliest known sundials date back to ancient Egypt, around 1500 BCE. These early devices were typically simple L-shaped instruments with a shadow-casting vertical component and a horizontal base marked with hour divisions. Egyptian obelisks may also have served as large-scale sundials, their long shadows providing a way to track time and divide the day. In Babylonia, where astronomical observation reached remarkable sophistication, sundials became tools not only for civil and agricultural use, but also for religious and astrological purposes. The Babylonians divided the day and night into 12 hours each, leading to the 24-hour day we still use today. In ancient Greece, sundials became increasingly refined. Greek mathematicians such as Anaximander and later Hipparchus applied principles of geometry and trigonometry to improve the accuracy and design of sundials. They understood that the gnomon had to be aligned with the Earth's axis and tilted at an angle corresponding to the local latitude to ensure accurate time division throughout the year. These innovations allowed sundials to account for seasonal variations in the sun's path, a challenge that earlier designs struggled with. By incorporating the mathematical understanding of celestial motion, the Greeks transformed sundials from mere observational instruments into tools grounded in theoretical science. The Romans inherited and further popularized sundial use, integrating them into public spaces such as forums and temples. Sundials became symbols of order, civic structure, and even imperial control over time. The famous Roman writer and architect Vitruvius described several types of sundials in his work, indicating a diversity of forms and functions. Some Roman sundials were portable, others were monumental. The Romans even developed the hemicyclium, a sundial carved into a hollow hemisphere with hour lines etched onto its interior surface, a design that could more accurately follow the curved path of the sun. Despite their ingenuity, sundials had significant limitations. Most notably, they depended on sunlight to function. Cloudy days, rain, and nighttime rendered them useless. Moreover, because sundials track the apparent motion of the sun rather than the uniform passage of time, they reflect what is known as solar time. Solar time varies throughout the year due to the elliptical shape of the Earth's orbit and the tilt of its axis, a discrepancy known as the equation of time. As a result, solar noon, when the sun is highest in the sky, does not occur at the same clock time every day. Without adjustment, sundials could be off by as much as 15 minutes depending on the season. To address these inaccuracies, ancient astronomers began to develop correction tables and theoretical models to align sundial readings with more consistent measures of time. This marked an early recognition that time, as humans wish to measure it, was not identical to the sun's motion. It suggested a growing abstraction that true time might differ from observed time. This abstraction would become increasingly important in the centuries to follow, as timekeeping moved from nature to mechanism, from shadow to gear. Sundials also played an educational and philosophical role. In many cultures, they were not just instruments, but symbols. Inscriptions on sundials often reminded viewers of the passage of time and the transience of life. Latin mottos such as Horas non numero nisi serenus, I count only the sunny hours, or Fugit ora, time flies, adorned Roman sundials. These aphorisms underscored the human relationship to time, both its measurement and its meaning. The sundial thus became a contemplative object, inviting reflection on mortality, change, and the rhythm of the cosmos. Culturally, sundials influenced architecture, city planning, and religious observance. Prayer times in Islamic culture, for instance, were originally aligned with solar positions, and sundials were instrumental in determining the correct times for daily prayers. In Christian Europe, monasteries used sundials to regulate the liturgical hours, ringing bells for matins, vespers, and other services. As a result, the sundial not only tracked the sun but also structured daily life, reinforcing collective routines and sacred rhythms. In Asia, sundials also held a place of importance. Ancient Chinese astronomers developed sophisticated mnemonic instruments for both civil and ceremonial use. Their designs often integrated with water clocks and astronomical towers, reflecting a holistic approach to timekeeping that blended observational accuracy with philosophical cosmology. In India, the Jantar-Mantar observatories built by Maharaja Jai Singh in the 18th century featured massive sundials capable of measuring time to within seconds, a testament to the enduring utility and symbolic power of solar instruments. Though eventually supplanted by mechanical clocks, sundials laid the conceptual and technical foundation for future timekeeping. They introduced the idea that time could be measured consistently and independently of specific events. They encouraged the development of geometry, astronomy, and observational methods. Most importantly, they marked the beginning of a transformation from a world in which time was felt and experienced to one in which time could be tracked, standardized, and ultimately controlled. This transition would not happen overnight, but the sundial stands as the earliest evidence of humankind's desire to tame the flow of time, to impose structure on the chaos of change, and to mark our place in the universe with lines drawn not in the sand, but in shadow. From these ancient shadows would eventually emerge the intricate gears of mechanical clocks, the vibrations of quartz crystals, and the oscillations of atoms, all driven by the same age-old pursuit to understand and master the invisible current that carries us forward. The development of mechanical clocks marked one of the most significant turning points in the history of timekeeping. While sundials had linked time to the motion of the sun and thus to the visible rhythms of the natural world, mechanical clocks introduced a new concept: the regulation of time through human-made mechanisms, independent of sunlight or celestial events. This transformation was not merely technical, it was conceptual. Mechanical clocks redefined time as something that could be measured evenly, continuously, and autonomously, something that ticked on, regardless of whether the sky was clear or clouded, whether the sun rose or set. It was the beginning of modern, abstract time. The roots of mechanical timekeeping stretch back to antiquity, with devices such as water clocks, also known as clepsydras, which used the steady flow of water to mark intervals of time. These were used in Babylon, Egypt, China, Greece, and Rome for timing speeches, regulating rituals, or determining night watches. While ingenious, water clocks were prone to inaccuracies due to temperature variations and inconsistent water flow. Still, they paved the way for the idea that time could be regulated mechanically rather than astronomically. The first true mechanical clocks began to appear in Europe in the late 13th and early 14th centuries. These early machines were massive, weight-driven structures installed in church towers and public squares. They used a system of gears and an escapement mechanism, a device that released energy in controlled intervals to turn a hand or strike a bell at regular times. One of the earliest known examples was constructed around 1283 in the monastery of Dunstable in England. By the 14th century, such clocks were appearing in cities like Milan, Paris, and London, marking the hours for public gatherings, markets, and prayers. The invention of the escapement was crucial. This mechanism allowed a steady release of energy from a weight or spring, which in turn drove the clock hands at a relatively consistent pace. The Virgin Foliot escapement, an early type, was far from perfect. It introduced irregularities and could vary significantly depending on temperature and friction, but it was a monumental advance over previous timekeeping methods. It enabled clocks to tick continuously without human intervention, laying the groundwork for more precise designs. Mechanical clocks quickly became central features of public life in medieval Europe. They were often installed in church towers, town halls, and marketplaces, not just to tell the time, but to symbolize civic order, religious discipline, and technological prowess. The sound of their hourly chimes echoed across towns and cities, structuring daily life and emphasizing the communal regulation of time. These early clocks did not yet have minute or second hands. They typically struck the hours alone, but this was enough to revolutionize social organization. One of the significant impacts of mechanical clocks was the increasing segmentation and standardization of time. In a world previously governed by flexible, event-based timing, where a task might be done at sunrise, at midday, or when the cows came home, clocks introduced rigid units. Activities were now scheduled for specific hours, regardless of daylight or context. Monasteries, already operating on a regimented schedule of prayers and work, embraced mechanical clocks to ring bells for the canonical hours. Over time, this mode of time discipline extended into commerce, labor, and governance. The rise of mechanical clocks coincided with profound economic and social changes in Europe, including the growth of urban centers, the expansion of trade networks, and the early stirrings of capitalism. Merchants needed reliable methods to coordinate transactions, plan shipments, and track labor. The ability to measure and divide time with mechanical regularity supported new modes of productivity and efficiency. Time began to acquire economic value. It could be sold, scheduled, wasted, or saved. The phrase, "time is money," would not appear until centuries later, but its roots were already being laid. By the 15th and 16th centuries, mechanical clockmaking had become a specialized and prestigious craft. Innovations such as the addition of clock faces, hour and minute hands, and spring-powered movements enabled smaller, more accurate, and portable timepieces. Wealthy individuals began commissioning clocks for their homes, transforming timekeeping from a public utility to a private possession. Clocks were no longer confined to towers. They entered parlors, studies, and personal chambers, further internalizing the regulation of time. The Renaissance period brought a renewed interest in science, mathematics, and precision. Clockmakers collaborated with astronomers and mathematicians to improve accuracy and incorporate astronomical data into their designs. Clocks were increasingly used for astronomical observations and navigation, with celestial models and planetary indicators built into elaborate timepieces. These devices reflected a growing sense that time was not only a practical concern, but also a subject of scientific inquiry, tied to the motion of the heavens and the fundamental structure of the universe. Perhaps the most transformative innovation of the mechanical clock era came in the 17th century with the invention of the pendulum clock by Dutch scientist Christian Huygens. Drawing on Galileo's earlier studies of pendular motion, Huygens designed a clock in 1656 that dramatically improved accuracy, from variations of 10 to 15 minutes per day to just 15 seconds. This invention would become the foundation of precise timekeeping for the next 2 centuries, but even before its arrival, the mechanical clock had already reshaped human life in profound ways. With mechanical clocks, time moved indoors, away from the sun and sky, into the realm of gears, springs, and regulated oscillations. It became detached from the natural world and increasingly uniform, linear, and abstract. This shift had psychological as well as social consequences. Time was no longer merely something experienced or observed. It was something enforced. Clocks did not just mark time. They ordered it, structured it, and imposed it. The bell that rang each hour was not a suggestion, but a command. The implications of this transformation were immense. In religion, it allowed more precise observance of rituals. In work, it enabled the regulation of labor and wages. In education, it structured the school day into fixed periods. In the sciences, it made possible new kinds of measurement and experimentation. In navigation, it laid the groundwork for solving the longitude problem, which required precise timekeeping to determine a ship's position at sea. In every sphere, the mechanical clock helped create a world that was more organized, more predictable, and more efficient, but also more constrained. Ultimately, mechanical clocks did more than tell time. They changed what time meant. They shifted our sense of time from the cyclical to the linear, from the communal to the individual, from the natural to the artificial. They introduced a sense of inevitability, of time as something that moves forward relentlessly, regardless of human will or cosmic intention. With each tick and tock, they trained generations to think of time not as something to live within, but as something to live by. The invention of the pendulum clock in the 17th century represented a monumental breakthrough in the science of timekeeping. It was a leap not only in mechanical engineering, but in the very way humanity understood and organized its relationship with time. For the first time, time could be measured with unprecedented accuracy, moving far beyond the crude approximations of earlier mechanical clocks. The pendulum itself is a deceptively simple object, a weight suspended from a fixed point so that it can swing freely under the influence of gravity. The key to its timekeeping potential lies in the regularity of its motion. Galileo Galilei, observing the swinging of a chandelier in a cathedral in Pisa in the late 16th century, discovered that the time it takes for a pendulum to swing is relatively constant, depending primarily on its length. He realized that the pendulum could serve as a natural regulator of motion, a kind of metronome dictated by the laws of physics rather than the imperfections of gears and weights. Though Galileo sketched a design for a pendulum clock, it was Christian Huygens who, in 1656, constructed the first working model. Huygens' pendulum clock reduced the daily error of timekeeping from about 15 minutes to less than a minute, and soon even greater accuracy was achieved. This marked the beginning of precision horology, the science of accurate timekeeping. The pendulum clock introduced a reliable rhythm into the measurement of time, transforming it into a predictable and quantifiable entity. It no longer merely mimicked the sun's path or approximated the hours. It defined them with mathematical certainty. This innovation profoundly influenced both scientific research and daily human behavior. The pendulum's reliability made it an essential tool for astronomers who needed precise time measurements to chart the stars, calculate planetary orbits, and verify celestial predictions. Observatories across Europe quickly adopted pendulum clocks to record astronomical events, and the synergy between clockmakers and scientists deepened. The accurate timing provided by pendulums allowed for more refined observations of the heavens, contributing directly to the development of Newtonian physics and the emerging understanding of gravitation and motion. As pendulum clocks became more refined, they also became more widespread. The introduction of anchor escapements, temperature-compensated pendulums, and innovations in materials enabled clockmakers to construct reliable, long-running clocks for public, domestic, and scientific use. Grandfather clocks, tall case clocks housing long pendulums and weight-driven mechanisms, became popular fixtures in European homes during the 17th and 18th centuries. They were both functional devices and status symbols, representing the owner's refinement, scientific awareness, and punctuality. With the spread of household clocks, the abstract, mechanical concept of time became part of everyday life. At the same time, innovations in spring-driven clocks enabled the miniaturization of timepieces. The mainspring, a coiled strip of metal that stored and released energy to drive a clock's mechanism, allowed clocks and watches to be made smaller and more portable. While spring-driven clocks had existed since the late 15th century, they became far more practical and accurate in conjunction with balance springs, also known as hairsprings, which were introduced in the 17th century by Huygens and Robert Hooke independently. The balance spring regulated the oscillations of the balance wheel, the functional equivalent of the pendulum in portable timepieces, allowing for precise time keeping even in a compact, mobile form. These developments led directly to the rise of the pocket watch, which became a fashionable and functional accessory for the elite and, eventually, for broader segments of society. Pocket watches were not just tools. They were symbols of personal order, responsibility, and modernity. To carry time with you was to demonstrate discipline and control. The segmentation of the day into minutes and, increasingly, seconds began to shape personal behavior and expectations. Schedules grew tighter. Punctuality became a virtue. The very tempo of life quickened. The newfound precision in timekeeping also played a pivotal role in solving practical and scientific challenges, particularly in navigation. One of the greatest challenges of maritime exploration in the 17th and 18th centuries was determining longitude, the east-west position of a ship at sea. Latitude could be found by observing the sun or stars, but longitude required knowing the exact time at a fixed reference point, such as Greenwich, and comparing it to the local time aboard the ship. A difference of 1 hour corresponded to 15 degrees of longitude. But until the development of highly accurate marine chronometers, no timepiece could survive the motion, temperature changes, and humidity of ocean travel without losing or gaining significant time. The British government's Longitude Act of 1714 offered a large monetary prize to anyone who could solve the problem. After decades of trial and innovation, John Harrison, an English clockmaker, succeeded in creating a series of marine chronometers that met the necessary accuracy for determining longitude. His work culminated in the H4 watch, completed in 1761, which revolutionized navigation and greatly improved the safety and efficiency of sea travel. This achievement was not just a technological feat, but a demonstration of how precision timekeeping could extend human reach across the globe. On land, the increasing accuracy of clocks enabled the coordination of large-scale economic and industrial systems. The 18th and 19th centuries saw the rise of factories, where labor was organized into shifts governed by the clock. Transportation systems, stagecoaches, railroads, and eventually buses and subways required timetables, which in turn depended on reliable timekeeping. Financial markets, postal services, and communication networks all came to rely on synchronized clocks. The world was becoming increasingly ordered around the ticking of machines. Culturally and psychologically, the pendulum and spring-driven clocks altered how people thought about time. Time was no longer simply a backdrop for events. It became a measurable, objective force that regulated daily life. People began to internalize the rhythms of the clock, structuring their activities in smaller, more precise intervals. The second hand on a clock face became a visual reminder of time's ceaseless flow, each tick a silent prod toward productivity, efficiency, and punctuality. Philosophers and writers of the time reflected on the new tyranny of the clock. While some praised the order and progress brought by precision timekeeping, others lamented the loss of natural rhythms and the increasing mechanization of life. Time was no longer just passing, it was being spent, managed, saved, or lost. The clock had moved from the tower to the pocket, and eventually to the human mind. The legacy of pendulum and spring clocks is enormous. They made possible the scientific revolution, global exploration, industrialization, and the entire framework of modern society. They helped reimagine time as a linear, divisible, and universal constant, a transformation that would later be challenged but never entirely undone. The pendulum's gentle swing and the spring's tight coil became metaphors for the newfound precision and control that defined the modern era. And though more advanced technologies would eventually surpass them, these clocks remain emblematic of humanity's quest to not only measure time, but to master it. The invention and expansion of the railroad in the 19th century fundamentally transformed how societies understood and used time. While pendulum and spring clocks had already brought precision to individual and domestic life, railroads demanded a new level of coordination and synchronization that went beyond local needs. For the first time, vast numbers of people and goods were moving rapidly across long distances, and the inconsistencies in local timekeeping, once relatively benign, became serious obstacles. This era marked the birth of standardized time, a revolutionary development driven not just by science or engineering, but by the pressing demands of industrialization and transportation. Before railroads, time was a local affair. Each town or city set its clocks by the sun, specifically by the local solar noon, when the sun reached its highest point in the sky. Because the Earth rotates at approximately 15 degrees per hour, solar noon occurs at different times in different places, even if they're only a few miles apart. This wasn't problematic in a world where most people rarely traveled far from home. Daily life was still largely governed by natural cycles, and minor variations in time between communities were of little consequence. Even early postal and stagecoach systems could accommodate some temporal imprecision. But the railroad changed everything. With trains traveling dozens or even hundreds of miles in a few hours, these local discrepancies became disruptive. A train might leave one city at 12 p.m. and arrive in another city to find that the local clocks read 12:14 p.m. or 11:47 a.m. Timetables became difficult to compile and even harder to follow. Miscommunications about departures and arrivals could lead to missed connections, delays, or, far more gravely, collisions. For a mode of transport that required tight scheduling and clear signaling, the lack of synchronized timekeeping was a dangerous flaw. Railroads forced the issue of time standardization. The need for a uniform time system became urgent, and it was the railway companies, not governments or scientists, who first took action. In Great Britain, the Great Western Railway began using London time, set by the Royal Observatory at Greenwich, for its operations as early as the 1840s. Other railway companies followed suit, and soon railway time became common across the country. At first, it coexisted awkwardly with local time. Clocks in town squares might show one time, while the railway station showed another, but over time, railway time began to dominate. By 1855, the vast majority of public clocks in Britain were set to Greenwich Mean Time, GMT, and in 1880, GMT was officially adopted as the standard legal time for the entire country. A similar process unfolded in the United States, but on a much larger scale. The U.S. spanned several degrees of longitude and had hundreds of rail lines operated by different private companies. Each city operated on its own local time, leading to a chaotic patchwork of over 50 local times in use by the 1870s. The result was not just confusion, it was near anarchy. The inability to coordinate schedules across companies and regions hampered efficiency and increased risk. Recognizing the growing crisis, American railway companies took matters into their own hands. On November 18, 1883, known as the Day of Two Noons, railroads across the United States implemented a system of standardized time zones. The country was divided into 4 time zones: Eastern, Central, Mountain, and Pacific. Each zone was based on a standard meridian of longitude, with time differing by exactly 1 hour from zone to zone. At exactly noon on that day, each railway station adjusted its clocks according to the new time standard. The public had little choice but to adapt. Although the U.S. federal government didn't officially adopt the time zone system until 1918, the railroad companies had already reshaped American time. This synchronization of time was not just a technical change. It was a profound cultural shift. People who had grown up with the sun as their timekeeper now live by clocks set to a standardized, abstract system that bore little relationship to local solar conditions. Noon was no longer when the sun was overhead, but when a clock said so, often based on the time in a city hundreds of miles away. This abstraction of time, begun by mechanical clocks and reinforced by the pendulum, reached a new level of artificiality and reach with the railroads. Time became detached from place. The implications extended far beyond transportation. Business hours, school schedules, factory shifts, postal deliveries, and telegraph operations all began to conform to standardized time. The pace of life accelerated and became more synchronized. The concept of punctuality took on new urgency and became a moral and social expectation. Clocks proliferated in public spaces and private homes, no longer as luxury items or symbols of refinement, but as practical necessities. Timekeeping became a public infrastructure, something society relied upon to function. The synchronization of time also raised questions of authority and control. Who decides what time it is? Before standardization, time was determined locally, often by religious or civic leaders. Now, time was dictated by distant observatories, national standards, or corporate policies. The centralization of time mirrored other forms of industrial and bureaucratic centralization that defined modern life. This shift provoked both awe and unease. For some, Standardized time was a triumph of rationality and progress. For others, it represented a loss of autonomy and natural rhythm. Beyond cultural and social transformations, the synchronization of time had scientific consequences. The ability to measure time precisely and consistently across distances was critical for advances in physics, especially in the study of motion and electromagnetism. Telegraph operators relied on synchronized time to timestamp messages. Astronomers could compare observations made in different locations. Surveyors and geographers could triangulate positions with greater accuracy. Standard time provided a shared temporal framework that enabled the growth of coordinated scientific inquiry across regions and continents. Yet, even as standard time unified human activity, it exposed a deeper truth: that time, as we use it, is a construct, a system created for convenience, not a direct reflection of nature. The Earth does not rotate in exactly 24 hours, and its orbit is not perfectly regular. The standardized time imposed by railroads and later reinforced by governments and international agreements is a carefully maintained illusion, one that requires continuous correction and management. The railroad age made time uniform, measurable, and centralized in a way that previous generations could not have imagined. It turned time into infrastructure, an invisible but essential system underlying modern civilization. The clock was no longer just a personal or communal tool. It became a social contract, binding strangers together across distances and ensuring that the world moved in coordinated rhythm. From the smoky platforms of 19th century train stations to the digital timetables of today's airports, that legacy continues. Standardized time, born of industrial necessity, became one of the defining structures of modern life. The invention of quartz clocks in the 20th century marked a revolutionary step in the evolution of timekeeping, bringing humanity closer to the dream of perfectly precise and stable measurement. Unlike mechanical timekeepers that relied on the oscillations of physical parts, pendulums, gears, and balance wheels, quartz clocks depended on the regular vibrations of a crystalline substance. This leap from mechanical to electronic timing fundamentally changed how we track, distribute, and experience time. It enabled mass production of reliable clocks, spurred the development of modern electronics, and laid the groundwork for digital technology and global synchronization. The principle behind quartz clocks is the phenomenon of piezoelectricity, discovered in the 1880s by Pierre and Jacques Curie. They found that certain crystals, most notably quartz, generate an electric charge when subjected to mechanical pressure. This effect also works in reverse. Applying an electrical voltage to such a crystal causes it to deform and vibrate at a highly regular frequency. These vibrations are extremely stable and can serve as a remarkably consistent timekeeping signal. For example, a standard quartz crystal used in watches vibrates at 32,768 times per second, a frequency that can be precisely counted and divided down to track seconds, minutes, and hours. Though the piezoelectric properties of quartz had been known for decades, it wasn't until 1927 that Warren Marrison and J.W. Horton, working at Bell Telephone Laboratories, constructed the first quartz clock. Initially large and confined to laboratories, these early quartz clocks were more accurate than anything the world had seen. While the best mechanical clocks of the era might drift by several seconds per day, quartz clocks reduced that drift to a fraction of a second. This level of precision stunned scientists and engineers alike, and it quickly became clear that quartz would become the new standard for timekeeping. In the decades that followed, especially after World War II, technological advances allowed quartz clocks to be miniaturized and mass-produced. By the 1960s and 1970s, quartz movements began to appear in consumer wristwatches and household clocks. Companies like Seiko in Japan and Bulova in the United States led the way, marketing quartz watches as symbols of modernity and reliability. The famous Seiko Astron, released in 1969, was the world's first commercial quartz wristwatch, and it marked the beginning of the so-called quartz revolution. This revolution was not merely a change in materials or mechanism. It represented a profound shift in accessibility and perception. Where mechanical timepieces were intricate, expensive, and often required regular maintenance or adjustment, quartz clocks were inexpensive, robust, and user-friendly. Accurate timekeeping became democratized. Almost overnight, the ability to know the exact time was placed within reach of the average person. No longer a luxury or an artisan product, the clock became ubiquitous, on wrists, in cars, on microwaves, in computers. The quartz clock was small enough to fit almost anywhere and cheap enough to be produced at scale. Timekeeping, once the province of kings, scientists, and wealthy merchants, had become universal. Beyond the consumer market, quartz technology had a transformative effect on scientific research, telecommunications, and global infrastructure. Laboratories used quartz oscillators to coordinate experiments, synchronize particle accelerators, and control spacecraft navigation. The telecommunications industry adopted quartz clocks to manage data transmission and switching operations, where even microsecond-level discrepancies could cause errors. The aviation industry used them to ensure safe air traffic coordination. Stock exchanges synchronized operations across continents. In essence, quartz clocks became the invisible heartbeat of the modern world, coordinating machines, people, and data with silent precision. What made quartz technology so successful wasn't just its accuracy, but its stability and resilience. Quartz oscillators were relatively unaffected by temperature changes, humidity, and physical shocks, issues that had long plagued mechanical timekeeping. Innovations such as temperature-compensated crystal oscillators, TCXOs, and oven-controlled crystal oscillators, OCXOs, pushed performance even further, achieving accuracies better than 1 second per year in commercial devices. High-end laboratory quartz clocks could outperform most mechanical systems by orders of magnitude. Despite their many advantages, quartz clocks were not infallible. Over long periods of time, even the best quartz oscillators could drift slightly due to aging of the crystal or environmental factors. Moreover, while they were sufficient for most practical purposes, scientific communities, particularly those involved in physics and astronomy, continue to demand ever higher precision. This ongoing quest for temporal accuracy eventually led to the development of atomic clocks, which would surpass even the most refined quartz technologies. But quartz remained the bridge between the mechanical past and the atomic future. Culturally, the arrival of quartz timekeeping helped solidify the sense of life as something measurable, scheduled, and quantified down to the second. The relentless accuracy of quartz-based devices reinforced the expectation that time was an objective and universally shared phenomenon. Digital watches, especially with the rise of liquid crystal displays, LCDs, replaced the analog dials of the past, subtly altering how people perceive time itself. Time no longer flowed in a circular motion across our hands, but in a linear stream of changing digits. This digital abstraction of time aligned with the broader trends of the information age, in which data, rather than sensation, became the dominant mode of understanding. The quartz revolution also foreshadowed the computational future. Quartz crystals became the time base for computers and digital devices, where precise timing is essential for operations, memory synchronization, and data processing. Every time a computer boots up, every time data is stored or transferred, every time you click a button on a digital device, it is quartz timing that keeps everything in sync. Without quartz clocks, modern computing and digital communication would be impossible. Thus, timekeeping moved beyond clocks and watches to become embedded in the core of every microchip and every network. In summary, the invention and proliferation of quartz clocks represented more than an improvement in accuracy. It was a paradigm shift. Quartz brought timekeeping from the realm of mechanical craftsmanship into the era of electronics, precision engineering, and global synchronization. It made exact time available to everyone, everywhere. It changed the cadence of modern life, facilitated the digital revolution, and became the standard against which newer, even more advanced technologies would measure themselves. Quartz timekeepers were not just tools. They were the silent scaffolding of an increasingly interconnected world. The invention of atomic clocks marked one of the most profound advancements in the history of timekeeping, taking precision to an entirely new scale and redefining the very definition of a second. While quartz clocks had already offered remarkable stability and accuracy, atomic clocks surpassed them by orders of magnitude. With their ability to measure time based on the vibrations of atoms, unaffected by temperature, pressure, or mechanical imperfections, atomic clocks became the new standard upon which modern science, navigation, communication, and even the global economy rely. The principle behind atomic clocks lies in atomic physics and quantum mechanics. Atoms, the fundamental units of matter, have electrons that occupy discrete energy levels. When an atom transitions between these levels, it absorbs or emits electromagnetic radiation at a specific and highly stable frequency. This frequency is not arbitrary. It is a natural constant, the same everywhere in the universe. This stability makes atomic transitions ideal for timekeeping. In 1949, the first atomic clock was developed at the U.S. National Bureau of Standards. It used ammonia molecules and was more of a proof of concept than a practical device. The real breakthrough came in 1955 when Louis Essen and Jack Perry at the National Physical Laboratory in the UK built the first practical cesium beam atomic clock. This device used the vibrations of cesium-133 atoms to measure time with unprecedented accuracy. Specifically, it counted the microwave radiation emitted by cesium atoms as they transitioned between two hyperfine energy levels in their ground state. The frequency of this transition, 9 billion cycles per second, was found to be remarkably stable and reproducible. This discovery had a revolutionary consequence. In 1967, the International System of Units officially redefined the second based on cesium atoms. No longer was a second derived from astronomical phenomena, such as the rotation of the Earth or the orbit of the Moon. Instead, a second was defined as the duration of 9 billion cycles of radiation corresponding to the transition between two energy states of a cesium-133 atom. Time, one of the most ancient and mysterious quantities, had been tied directly to the behavior of matter at the quantum level. Atomic clocks ushered in an era of scientific precision and enabled technologies that had previously been impossible. One of the most important applications was in satellite navigation, particularly the Global Positioning System. GPS relies on a constellation of satellites, each equipped with atomic clocks, broadcasting the precise time. A GPS receiver on Earth calculates its position by comparing the time signals from multiple satellites. Because radio signals travel at the speed of light, even a microsecond of error could result in location inaccuracies of hundreds of meters. Only atomic clocks are accurate enough to support this system. Without them, GPS would not function. Beyond navigation, atomic clocks play a critical role in telecommunications, power grids, high-frequency trading, and global scientific research. Telecommunications networks require synchronization down to billionths of a second to ensure data integrity. Power grids rely on precise timing to balance supply and demand, and avoid blackouts. Financial markets depend on accurate timestamps to settle trades and maintain fairness. Scientific experiments, especially in astronomy and particle physics, require synchronized timing across multiple observatories or detectors, sometimes located on opposite sides of the Earth. Atomic clocks also allow for rigorous tests of fundamental physical theories, particularly Einstein's theory of relativity. According to general relativity, time runs differently depending on the strength of gravity, a phenomenon known as gravitational time dilation. Clocks on airplanes, satellites, or mountaintops run at different rates compared to those at sea level. Atomic clocks are so precise that they can measure these differences directly, confirming the predictions of relativity with exquisite accuracy. For instance, GPS satellites must regularly correct for both special and general relativistic effects, or their positioning would quickly become inaccurate. Over the decades, atomic clocks have continued to improve. New types of atomic clocks have been developed using different atoms and more advanced technologies. Hydrogen maser clocks offer excellent short-term stability. Rubidium clocks, though slightly less accurate, are compact and widely used in commercial systems. More recently, optical lattice clocks, using atoms like strontium or ytterbium and operating at optical frequencies, have achieved even greater precision. These optical clocks measure transitions at much higher frequencies than cesium, allowing for finer resolution and potentially redefining the second again in the near future. These modern atomic clocks are so precise that they would lose or gain less than a second over the entire age of the universe. This level of exactness is mind-boggling, and it raises philosophical as well as technical questions. What does it mean to measure time this precisely? Do we need this kind of accuracy? The answer lies in the ongoing evolution of science and technology. As we probe the universe more deeply, communicate more globally, and operate on faster and finer scales, the need for exact timing becomes ever more essential. In addition, atomic clocks contribute to our understanding of the universe itself. They are used in studies of gravitational waves, tests of whether fundamental constants are truly constant, and searches for dark matter. Some theoretical models predict that changes in dark matter fields could cause tiny variations in atomic transition frequencies. Only atomic clocks are sensitive enough to detect such minute changes, offering a new window into fundamental physics. Despite their technical complexity, atomic clocks symbolize humanity's desire to master time, to pin down the elusive flow that governs all motion and change. They bridge the world of the incredibly small, quantum states of atoms with the vast and complex systems of global civilization. They stand as monuments to scientific achievement, uniting theory and practice in a device that counts the invisible pulses of the universe. As we move forward, atomic clocks will continue to shape our technological and scientific landscape. They will likely evolve into even more compact, efficient, and precise forms. Miniaturized atomic clocks are already being integrated into mobile devices, enabling new kinds of location services and timing applications. Space-based atomic clocks will enable deep space navigation for future missions to Mars and beyond. Ultimately, atomic clocks represent the most precise way humans have ever found to measure the invisible flow of time. They reflect not only our technical capabilities, but also our deeper quest to understand the structure of reality. By capturing the rhythm of atoms, we have brought time under extraordinary control, revealing not just what time is, but what it can enable when measured with near perfection. The development of Einstein's theory of relativity in the early 20th century radically transformed our understanding of time, challenging centuries of intuitive and scientific belief in its uniformity and absolute nature. Prior to Einstein, time was considered a constant backdrop to all events. ticking away identically for all observers regardless of their motion or position. Newtonian physics treated time as universal, marching forward at the same rate for everyone, everywhere. But Einstein's theory shattered this concept, revealing that time is not an immutable stage upon which reality unfolds, but a dynamic and flexible dimension that is influenced by speed, gravity, and motion itself. The two pillars of Einstein's revolution were the special theory of relativity, 1905, and the general theory of relativity, 1915. Both had profound implications for the nature of time. Special relativity introduced the idea that time is relative to the observer's frame of reference. This means that the passage of time depends on how fast an object is moving relative to the speed of light. According to the famous equation delta t equals delta t slash square root 1 b superscript 2 slash c superscript 2, as an object approaches the speed of light, c, time slows down relative to an observer at rest. This phenomenon, called time dilation, means that a clock aboard a fast-moving spacecraft would tick more slowly than one on Earth. General relativity expanded on this concept by introducing the influence of gravity. According to Einstein's new model of the universe, massive objects like stars and planets warp the fabric of space-time, and this curvature affects the flow of time. The stronger the gravitational field, the more time slows down. This is gravitational time dilation. A clock closer to a massive object runs slower than one farther away. In other words, time passes more slowly in stronger gravitational fields. These predictions, initially theoretical, have been experimentally verified with remarkable precision. One of the most compelling demonstrations of time dilation came from the Haffel-Keating experiment in 1971, when atomic clocks were flown around the world on commercial airliners. Upon comparing the clocks after the flights, researchers found measurable differences consistent with both special and general relativity. Time had indeed moved differently, depending on speed and altitude. The practical consequences of these discoveries are not merely academic. They are embedded in the technologies we use every day. Perhaps the most dramatic example is the Global Positioning System. GPS satellites orbit Earth at high speeds and altitudes, and therefore experience both forms of time dilation. They move faster, special relativity, and are farther from Earth's mass, general relativity. The result is a net gain of about 38 microseconds per day compared to clocks on Earth. While this may seem insignificant, the accuracy of GPS depends on nanosecond precision. Without compensating for these relativistic effects, GPS positions would quickly drift by kilometers, rendering the system useless. That engineers routinely adjust satellite clocks for relativistic time differences is a striking testament to the real-world impact of Einstein's theories. Einstein's reconceptualization of time also had profound implications for cosmology and philosophy. It introduced the idea that time is not a separate entity from space, but part of a unified four-dimensional continuum called space-time. Events occur not merely at a location in space, but at a location in both space and time. This shift forced physicists to abandon the idea of an objective, universal now. In the relativistic universe, what one observer sees as simultaneous might appear as happening at different times to another observer. The notion of simultaneity, long taken for granted, was revealed to be observer-dependent. This relative nature of time deeply challenges our everyday experience. For humans, time feels like a steady flow, moving from the past to the future through a present moment. But in the relativistic view, all points in time, past, present, and future, exist equally within the fabric of space-time. This view is known as the block universe model, in which time is not a flowing river, but a landscape in which all events are laid out and simply experienced differently depending on one's trajectory through space-time. This concept has provoked intense philosophical debate. If the future already exists in the same way as the past, does that mean the future is predetermined? Is free will compatible with a static space-time? While these questions remain open, they underscore the extent to which relativity has reshaped not just scientific understanding, but fundamental notions of reality. Einstein's theory has also laid the foundation for some of the most speculative ideas in physics. For example, the warping of space-time by gravity raises the theoretical possibility of time travel. Certain solutions to Einstein's equations, like the famous Gödel metric or hypothetical constructs such as wormholes, suggest that it might be possible, at least mathematically, to travel to the past or the future. These ideas remain highly speculative and fraught with paradoxes, but they are a direct consequence of treating time as a malleable dimension rather than a fixed background. In the century since Einstein first published his theories, relativity has withstood every experimental test. From the behavior of particles in accelerators to the observation of gravitational waves, the predictions of relativistic time have been borne out time and again. Yet despite its extraordinary success, relativity has not answered all our questions about time. Most notably, it remains in tension with quantum mechanics, which treats time differently. While relativity sees time as part of a continuous geometric fabric, quantum mechanics often treats it as a parameter, a passive backdrop against which particles evolve probabilistically. Reconciling these views remains one of the deepest challenges in theoretical physics. Even so, the legacy of relativity in reshaping our understanding of time is indisputable. It showed us that time is not universal, not absolute, and not independent of the physical world. It can be stretched, compressed, and distorted by motion and gravity. It proved that time is intimately woven into the structure of the cosmos, not merely a measure of change, but a participant in the dynamics of the universe itself. In practical terms, relativity enables the precision technologies on which modern life depends. In conceptual terms, it forces us to rethink what we mean by time. It invites us to imagine a universe where time is not the same for everyone, and where the past and future may not be as distinct as we once believed. It reminds us that our deepest intuitions can be upended by the elegance of mathematics and the rigor of experiment. In doing so, the theory of relativity did not diminish the mystery of time, it deepened it. And it continues to challenge us to explore the true nature of the dimension that governs our existence. In the quantum realm, where particles behave like waves and outcomes are governed by probabilities rather than certainties, time emerges as a particularly elusive and enigmatic concept. While relativity treats time as a flexible, geometric feature of space-time influenced by gravity and motion, quantum mechanics seems to regard time quite differently, almost as an external, immutable parameter. This mismatch between how time is treated in the two foundational theories of modern physics presents one of the deepest unresolved issues in science. Understanding time in quantum mechanics not only reveals the strangeness of the microscopic world, but also exposes the profound conceptual divide between two otherwise remarkably successful descriptions of nature. At the heart of quantum mechanics is the Schrödinger equation, a mathematical formula that describes how the state of a quantum system evolves over time. The equation takes the form IH del psi / del t equals H psi. In this expression, psi represents the wave function, a complex mathematical object encoding all the possible information about a quantum system. H is the Hamiltonian operator, which represents the total energy of the system. And T, crucially, is time. Here, time acts as a fixed background parameter, not something that is affected by the system itself. It serves merely as a clock ticking outside the system, guiding the evolution of its state. This treatment of time is fundamentally different from general relativity, where time is dynamic, shaped by energy, matter, and geometry. In quantum mechanics, particles can be in superpositions of different states. They can exist in multiple places or have multiple energies simultaneously. But the time parameter in the Schrödinger equation does not possess such quantum ambiguity. It remains classical and unchanging. This asymmetry has long puzzled physicists and philosophers alike. One of the consequences of this treatment is that quantum mechanics lacks a time operator, a formal way to define time as a quantum observable, like position or momentum. In most formulations, one cannot measure time the way one measures other physical quantities in quantum theory. Attempts to define such an operator have run into fundamental difficulties. For example, time does not have a discrete spectrum in the way energy or position can. It cannot be treated as a physical observable in the standard framework. This has led to the realization that time, in quantum mechanics, is not a property of systems, but a condition imposed upon them. This creates an inherent tension when trying to develop a theory that unifies quantum mechanics with general relativity. If time is a rigid, external input in one theory but a dynamic, internal result in the other, how can the two be reconciled? This problem becomes particularly acute when we try to describe the entire universe quantum mechanically, as in quantum cosmology. If there is no outside observer to supply a time parameter, then what does it even mean for the universe to evolve? One approach to resolving this issue has been to look for formulations of quantum theory where time is not fundamental, but emergent. In such theories, time might arise from correlations between quantum states, rather than being built into the laws themselves. A notable example is the Wheeler-DeWitt equation, a candidate for a quantum version of general relativity. This equation, strikingly, contains no explicit time variable at all. Known as the timeless equation, it suggests that at the most fundamental level, the universe might not evolve in time as we perceive it, but instead be described by a static wave function containing all possible configurations of reality. In this timeless view, what we perceive as the flow of time might be an illusion, an emergent phenomenon arising from our interaction with a particular subset of the universe's configurations. In other words, time might not be a feature of the fundamental laws, but a useful approximation that appears in certain contexts, particularly those involving classical observers like ourselves. Some interpretations of quantum mechanics, like the relational or consistent histories approaches, explore these ideas in depth. Another area where the intersection of time and quantum mechanics becomes especially strange is in quantum entanglement and non-locality. In experiments with entangled particles, a measurement made on one particle appears to instantaneously affect the state of its partner, regardless of the distance between them. These correlations seem to transcend space and time, violating classical intuitions about causality. While this doesn't allow faster-than-light communication, it suggests that quantum information might be fundamentally non-temporal, that quantum systems can share connections that are not bound by the usual flow of time. Quantum mechanics also challenges our understanding of causality. In the classical world, causes precede effects, and time flows in one direction. But in quantum mechanics, particularly in experiments involving delayed choice or quantum erasure, the sequence of events can become ambiguous. In some interpretations, the outcome of a measurement in the present can appear to influence the behavior of a particle in the past. These are not violations of causality in a strict sense, but they underscore how the quantum world does not adhere to the familiar temporal logic of macroscopic experience. Adding to the complexity is the so-called measurement problem, the question of what constitutes a quantum measurement and how wave function collapse occurs. During a measurement, A quantum system transitions from a superposition of states to a single, definite outcome. But this process seems to require an external observer and an external clock. When, exactly, does the collapse happen? How long does it take? These questions have no clear answers within standard quantum theory, and they further highlight the ambiguous role of time in the theory. Recent advances in quantum information theory have provided new ways of thinking about these problems. Time, in some formulations, is treated as a type of information, something that emerges from the entanglement structure of quantum states. There are even theoretical proposals for constructing quantum clocks within a larger system, in which time is defined relative to the correlations between subsystems rather than by an external variable. Despite these advances, the problem of time in quantum mechanics remains unsolved. No consensus exists on whether time is fundamental or emergent, whether it should be treated as an observable or a parameter, or how to fully reconcile its role with general relativity. Physicists continue to explore new mathematical frameworks, such as loop quantum gravity, string theory, and the holographic principle, in hopes of finding a theory of quantum gravity that can explain time in a unified way. In the end, quantum mechanics reveals that our classical understanding of time, as a smooth, continuous progression, is an approximation that breaks down at small scales. At the quantum level, time may not flow at all. It may not even exist as we understand it. Instead, it might be a construct, a convenient way to organize our observations, but not an intrinsic feature of reality. This deeply unsettling idea pushes the boundaries of both physics and philosophy. It challenges not only how we measure time, but what it means to experience it. Quantum mechanics has shown us that the fabric of reality is far stranger than we ever imagined, and time, the very dimension in which we live, may be one of its greatest mysteries. The question of time's origin is one of the most profound in all of science and philosophy. While classical physics assumed that time stretches infinitely in both directions, modern cosmology has upended this view. The discovery of the Big Bang and the development of general relativity have given rise to the radical idea that time itself might have a beginning, a moment when not only matter and space, but time as well, came into existence. In this view, asking what happened before the Big Bang may be as meaningless as asking what's north of the North Pole. For the first time in history, science offered a model where time had a starting point and possibly a limit to its future as well. The foundation of modern cosmology rests on Einstein's general theory of relativity, which reimagines gravity as the curvature of space-time caused by mass and energy. Using this framework, in the 1920s, Alexander Friedman and Georges Lemaitre independently derived models of an expanding universe. These theoretical insights were later supported by Edwin Hubble's observation in 1929 that distant galaxies are moving away from us, indicating that the universe is expanding. If we rewind this expansion, it leads to a singular point of infinite density and temperature, a state now known as the Big Bang. But the Big Bang was not an explosion in space. It was an expansion of space itself. More importantly, it was also the beginning of time as we understand it. According to current models, the universe is around 13.8 billion years old. This number doesn't just refer to the age of the matter in the universe, but to the age of time itself. Before that, if before even makes sense, there was no time in the conventional sense. Time emerged with the universe, suggesting it is not an external container in which the cosmos exists, but something that began with it. This view is consistent with general relativity, which does not require time to exist outside the bounds of the universe. However, it leads to deep philosophical and physical questions. Can time have a beginning without a cause? What does it mean for something to begin if there was no before? These questions challenge the limits of human language and conceptual frameworks, and they blur the line between physics and metaphysics. Some physicists and cosmologists have explored alternative models that attempt to describe what, if anything, came before the Big Bang. One idea is the concept of a cyclical universe. In these models, the universe undergoes infinite cycles of expansion and contraction, big bangs followed by big crunches, and then rebirth. Time in this model is not linear with a singular beginning, but circular, eternal, and recursive. This idea can be traced back to ancient cosmologies, but has also gained some traction in modern theoretical physics, particularly in string theory and loop quantum cosmology. Other proposals, such as the no-boundary model by Stephen Hawking and James Hartle, suggest that the universe may be finite, but without boundaries. In this view, time near the Big Bang transitions into a kind of space-like dimension, making the concept of a temporal beginning obsolete. Just as the Earth's surface is finite but has no edge, time could be finite, but without a sharp beginning point. This requires the application of quantum principles to space-time itself, suggesting that near the origin, classical notions of time and space cease to apply and are replaced by a more abstract, probabilistic framework. There are also multiverse theories which posit that our universe is just one of many, each with its own timeline and physical laws. In this scenario, what we perceive as the beginning of time might be a localized event within a much larger and older, perhaps eternal, meta-reality. These models are highly speculative and currently beyond empirical verification, but they attempt to account for the fine-tuning of our universe and the nature of cosmic origins. From an observational standpoint, cosmologists use the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang, as a kind of fossil record of the early universe. By analyzing the tiny fluctuations in the CMB, scientists can infer the density, geometry, and expansion history of the cosmos. These observations help refine our understanding of cosmic time, especially in the moments immediately following the Big Bang, when time and space were undergoing rapid inflation. Interestingly, the earliest epochs of the universe, especially the first Planck time, around 10 superscript 3 seconds after the Big Bang, are still shrouded in mystery. At this scale, quantum effects dominate, and classical descriptions of time break down. We currently lack a complete theory of quantum gravity that can describe this phase with accuracy. Without such a theory, the true nature of time at the universe's origin remains speculative. Another intriguing question concerns the arrow of time. Why does time seem to flow in one direction, from past to future? This asymmetry is not obvious from the fundamental laws of physics, most of which are time-symmetric. The prevailing explanation ties the arrow of time to the concept of entropy from the second law of thermodynamics. The universe began in a state of extremely low entropy, and over time, entropy has increased, giving us the perception of time's forward progression. But why the universe began in such a low entropy state is still unknown. It may be a boundary condition or a clue to deeper laws yet to be discovered. Cosmology also allows us to speculate on the ultimate fate of time. Depending on the universe's expansion dynamics, time might continue indefinitely or come to an end. If the universe continues to expand forever, stars will eventually burn out, galaxies will drift apart, and entropy will reach a maximum, a heat-death scenario in which no further work can be done, and time loses all practical meaning. Alternatively, if the universe recollapses in a big crunch, time might come full circle. There are even speculative models where time could reverse under extreme conditions, though such ideas remain highly theoretical. In recent years, some physicists have proposed radical alternatives to our understanding of time. The emergent time hypothesis, for example, suggests that time is not fundamental but arises from deeper timeless laws of quantum mechanics or string theory. In this view, time is not a pre-existing dimension but an emergent property of entangled quantum states. This idea aligns with some interpretations of the Wheeler-DeWitt equation, which, as mentioned earlier, contains no explicit time parameter. In such models, time may not have begun at all. It may be an illusion, an artifact of our limited perspective within a vast, timeless reality. Ultimately, cosmology has revealed that time is far more complex and mysterious than we ever imagined. It may have a beginning, or it may not. It may be fundamental, or it may be emergent. It may flow eternally, or it may vanish altogether. Our best models continue to evolve, guided by new observations and deeper theoretical insights. But one thing is clear. Any complete understanding of the universe must include not just a theory of matter and energy, but a theory of time itself. In probing the cosmos, we are also probing the nature of our own existence. Time is not just the backdrop for the universe's story, it is a central character in the narrative. And as we look further into space and deeper into the structure of reality, we are continually reminded that time may not be what it seems. While physics has provided increasingly precise and abstract definitions of time, humans experience it in a very different way, biologically and psychologically. From the rhythmic beating of the heart to the internal perception of waiting, rushing, or aging, our relationship with time is deeply rooted in our biology and shaped by subjective mental processes. Science has shown that time is not only measured by clocks and equations, but also by cells, neurons, and memories. This experiential dimension of time reveals yet another layer to the complex nature of temporal reality, bridging the objective and subjective, the measurable and the felt. At the biological level, time is most closely linked to what are known as circadian rhythms, internal biological clocks that govern cycles of sleep and wakefulness, hormone production, body temperature, metabolism, and other physiologichical functions. These rhythms, roughly 24 hours in length, are driven by a group of neurons in the hypothalamus called the suprachiasmatic nucleus, SCN. Located just above the optic chiasm, the SCN receives direct input from the eyes and synchronizes the body's internal rhythms to the external light-dark cycle of the Earth's rotation. The molecular basis of these circadian rhythms has been extensively studied. Within individual cells, a feedback loop involving genes and proteins regulates the timing of various physiological activities. Key genes, such as clock and BMEL1, turn on the expression of other genes, which in turn inhibit their own expression after a delay, creating oscillations that form the cellular clock. These molecular cycles are remarkably consistent across many species, from fruit flies to humans, demonstrating the evolutionary importance of keeping time internally. Disruptions to the circadian system, such as through shift work, jet lag, or artificial lighting, can have serious consequences for physical and mental health. Sleep disorders, depression, metabolic syndrome, and even cancer have been linked to the desynchronization of biological clocks. This shows that our bodies do not simply respond to time. They actively keep track of it, and our well-being depends on the alignment of internal time with external cycles. But beyond the circadian scale, humans also have a complex psychological relationship with time. Unlike clocks, we do not perceive time in steady, uniform increments. Instead, our sense of time is highly elastic and influenced by attention, emotion, memory, and context. Time can seem to slow down during moments of intense fear or danger, and speed up during periods of deep engagement or joy. Conversely, boredom and pain can make time feel excruciatingly long. This variability in time perception is rooted in brain function. One of the key areas involved is the basal ganglia, which interacts with the prefrontal cortex to estimate intervals and durations. The neurotransmitter dopamine plays a crucial role in modulating these estimates. High levels of dopamine are associated with a faster internal clock, leading people to perceive time as moving more quickly, while low levels tend to slow down this internal sense. This helps explain why certain neurological conditions, like Parkinson's disease, which involves dopamine deficits, also affect time perception. Memory also shapes our experience of time. The psychologist William James famously distinguished between two aspects of time: the specious present, the short duration we are consciously aware of, and our memory-based sense of time over longer periods. Our retrospective sense of how long something lasted is heavily influenced by how many memorable events occurred during that period. A day packed with novel experiences may seem longer in hindsight than a routine day, even if it felt shorter while it was happening. This helps explain why time seems to move faster as we age. New experiences become rarer, and our brains form fewer distinct memories, compressing our retrospective sense of time. Children, on the other hand, perceive time as slower. Their brains are constantly encoding new information, their attention spans are different, and their internal clocks may run at a different pace. This contributes to the common childhood impression that summers last forever, while adults often feel the years fly by. Language and culture further influence psychological time. Some languages use spatial metaphors to describe time, thinking of the future as ahead and the past as behind, while others conceptualize it vertically or even in reverse. Cultural attitudes toward punctuality, patience, and planning also shape how people experience time. In some cultures, time is viewed as a scarce commodity that must be efficiently managed. In others, it is treated more fluidly, with an emphasis on presence and relational depth over strict scheduling. There is also the distinction between monochronic and polychronic time orientation, terms introduced by anthropologist Edward T. Hall. Monochronic cultures, such as those in much of Western Europe and North America, value punctuality, scheduling, and doing one task at a time. Polychronic cultures, more common in Latin America and the Middle East, are more flexible with time, placing higher value on human interaction than adherence to schedules. These cultural attitudes reflect how social structures shape and are shaped by perceptions of time. Biological and psychological time are also central to the philosophy of consciousness. One of the defining features of conscious experience is the flow of time, the sense that we move from one moment to the next, that there is a past behind us and a future ahead. This continuity is essential to our identity. Some neuroscientists suggest that consciousness itself may be built around a temporal structure, a continuous integration of sensory information, attention, and memory that constructs the feeling of now. Without the ability to sense time, our conscious experience would be radically different, perhaps even impossible to describe. Time also plays a central role in trauma and mental health. In post-traumatic stress disorder, PTSD, for example, traumatic events can become stuck in memory, leading sufferers to relive the past as though it is still happening. In depression, the future may seem closed off or meaningless, distorting the natural flow of time and making recovery difficult. These conditions highlight how fragile and essential our internal sense of time really is. As we age, time becomes even more central to our identity. Aging is not merely the accumulation of biological changes, but a transformation in how we perceive and relate to time. Older adults often become more future-conscious, reflective, or nostalgic. Developmental psychologists note that our goals, values, and motivations change depending on our time horizon. Young people tend to prioritize exploration and novelty, while older adults often value emotional fulfillment and legacy. These shifts illustrate that time is not just a measurement, it is a lens through which we view our lives. In sum, while physics gives us objective measures of time, biology and psychology reveal how we actually live it. Our bodies track time through molecular cycles and neurological circuits. Our minds interpret time through attention, memory, and emotion. Time is both an external dimension and an internal experience. And though the seconds may tick uniformly on a clock, they do not tick the same in our hearts and minds. This intersection of biology and psychology with time adds richness to our understanding of what time truly is. It shows that time is not only a fundamental feature of the cosmos, but also a deeply human reality, shaped by light and darkness, neurons and hormones, joy and sorrow. To know time, then, is not only to study the stars or atoms, but to understand ourselves. In our interconnected and technologically dependent world, the need for standardized, precise, and universally recognized timekeeping has never been greater. From financial markets executing trades across global time zones to satellite communications and GPS systems requiring nanosecond-level synchronization, modern civilization relies on a unified framework of time. That framework is no longer governed by sundials or pendulums, but by atomic oscillations, international agreements, and carefully maintained scientific protocols. The science of modern timekeeping is an intricate, collaborative effort that blends physics, engineering, and global coordination. The foundation of current timekeeping lies in the second, the base unit of time in the International System of Units, SI. Historically, the second was defined as a fraction 1/86 for 100 of a solar day, which is the time the Earth takes to rotate once relative to the Sun. However, Earth's rotation is not perfectly uniform. It is subject to irregularities due to tidal friction, seismic activity, and long-term geophysical processes. These fluctuations make solar time an unreliable foundation for high-precision scientific and technological applications. To resolve this, in 1967, the General Conference on Weights and Measures redefined the second in terms of atomic time. Specifically, the second is now defined as the duration of 9,192,631,770 oscillations of radiation corresponding to the transition between two hyperfine energy levels of the ground state of the cesium-133 atom. This atomic definition provides a universal, stable, and reproducible standard that is independent of the Earth's rotation or any astronomical phenomena. Atomic clocks based on cesium atoms became the gold standard for timekeeping. These devices exploit the fact that atoms of the same element oscillate at the same frequency under the same conditions, providing a natural and highly consistent timekeeper. The most precise atomic clocks today are accurate to within a few billionths of a second per day. Some newer designs, like those using optical lattice clocks with strontium or ytterbium atoms, are even more precise, potentially deviating less than 1 second over the lifetime of the universe. These highly accurate atomic clocks form the basis of International Atomic Time, TAI, a continuous timescale calculated by combining the readings of over 400 atomic clocks operated in more than 70 laboratories around the world. TI is not adjusted for the Earth's irregular rotation. It provides a smooth, uninterrupted scale of time, ideal for scientific and technical use. However, civil time, the time shown on clocks and used in daily life, needs to stay in sync with the rotation of the Earth because that's how we experience day and night. This synchronization is handled by Coordinated Universal Time, UTC, which is derived from TEI but occasionally adjusted by adding or subtracting leap seconds. Leap seconds are introduced to account for the gradual slowing of Earth's rotation and keep UTC within zero point 0.9 seconds of universal time, which is based on direct astronomical observations. The addition of leap seconds is decided by the International Earth Rotation and Reference Systems Service, typically announced several months in advance. These adjustments are usually made at the end of June or December. Since the introduction of leap seconds in 1972, more than 24 have been added. However, this practice is not without controversy. The unpredictability and irregularity of leap seconds can cause problems for computer systems, GPS satellites, and financial software that depend on continuous, uniform timekeeping. As a result, there are ongoing discussions about abolishing leap seconds altogether and allowing UTC to gradually drift from astronomical time. Another important aspect of modern timekeeping is the role of the Bureau International des Poids et Mesures, located near Paris, France. This organization is responsible for maintaining international time standards, coordinating with national laboratories, and publishing the official values of TI and UTC. The BIPM ensures that time remains consistent, synchronized, and accessible across the globe. In practical terms, global synchronization is achieved through a range of technologies. The Global Positioning System, for example, relies on atomic clocks aboard satellites to provide precise timing data. Each GPS satellite broadcasts its time signal, which, when compared to signals from other satellites, allows a GPS receiver to determine not just position but also the exact time. GPS time is closely aligned with UTC, although it does not implement leap seconds, which can lead to small discrepancies that must be corrected algorithmically. The Network Time Protocol, NTP, is another crucial system used to synchronize clocks on computer networks. Operating over the Internet, NTP ensures that devices, ranging from smartphones to financial servers, remain in close alignment with official time sources. For highly sensitive applications, more accurate protocols like the Precision Time Protocol, PTP, or even direct access to atomic clocks may be used. Beyond technology and infrastructure, the social and legal recognition of time standards also matters. Most countries adopt UTC as the basis for their national legal time, adjusting it with time zones and daylight saving time practices. This legal time governs everything from court deadlines to train schedules to financial transactions. Discrepancies or failures in timekeeping can have serious economic, legal, and operational consequences. The precision of modern timekeeping has also opened the door to new scientific possibilities. For example, time dilation effects predicted by Einstein's theories of relativity are no longer just theoretical. They are observed and accounted for in real systems. Atomic clocks flown on airplanes or placed on mountaintops run slightly faster than those at sea level, in accordance with general relativity. GPS systems correct for both special and general relativistic effects to maintain their accuracy. These adjustments are so routine that they often go unnoticed, yet they represent a profound merging of theoretical physics and everyday technology. Furthermore, precise timekeeping has become a tool in other branches of science. In geology and seismology, time-synchronized sensors detect and analyze earthquakes. In astronomy, precisely timed observations of pulsars, rotating neutron stars that emit regular bursts of radiation, allow scientists to probe the structure of space-time and search for gravitational waves. In telecommunications, time synchronization is critical for data packet transmission, call handoffs, and secure encryption protocols. As timekeeping continues to evolve, researchers are developing next-generation clocks based on optical frequencies, which oscillate much faster than microwave-based cesium clocks. Optical lattice clocks and ion-based clocks, with their extraordinary stability and low sensitivity to environmental disturbances, could become the new standard. These devices can measure gravitational potential differences over very short vertical distances, effectively acting as time gravimeters. This has exciting implications for geophysics, environmental monitoring, and tests of fundamental physical theories. In conclusion, modern timekeeping is far more than just keeping clocks running on time. It is a vast, interconnected system that touches every aspect of modern life, from personal electronics to the infrastructure of science and commerce. The redefinition of the second, the coordination of global atomic clocks, the integration of relativistic corrections, and the continuous pursuit of higher precision all point to time as not merely a convenience, but a critical foundation of modern civilization. Time, once measured by shadows and bells, is now defined by the oscillations of atoms and regulated by international science. And yet, with all this precision, our quest for ever better timekeeping continues. We now live not just by the hour or minute, but by the nanosecond and beyond, a reflection of how deeply embedded the science of time has become in the rhythm of contemporary life. As humanity's need for ever greater temporal precision accelerates alongside technological progress, the future of timekeeping is poised for a revolutionary transformation. While atomic clocks based on cesium 133 have served as the international standard since the mid-20th century, newer technologies rooted in the principles of quantum mechanics and optical physics promise to redefine how we measure, experience, and apply time. These emerging systems, such as quantum clocks and optical lattice clocks, not only offer unprecedented accuracy, but also open the door to profound new scientific questions about the nature of time itself. One of the most promising advancements in this field is the development of optical lattice clocks. Unlike cesium clocks, which rely on the microwave frequencies associated with cesium atom transitions, optical lattice clocks use atoms like strontium or ytterbium, which oscillate at much higher frequencies in the optical part of the electromagnetic spectrum. Because these oscillations occur hundreds of thousands of times faster than those in the microwave range, they allow for finer resolution and more stable timekeeping. In practical terms, an optical lattice clock could be so precise that it would not gain or lose a second over the entire lifespan of the universe. These clocks function by trapping a large number of atoms in a grid of laser beams, the lattice, which holds them nearly motionless in place, minimizing disturbances. A second laser then probes the atoms to measure their resonance frequency with extreme precision. Because many atoms are measured simultaneously, noise is reduced and statistical accuracy improves. These devices are already outperforming traditional cesium clocks and are strong candidates for becoming the next generation of time standards. In parallel, quantum logic clocks represent another cutting-edge approach. Developed by manipulating single ions, charged atoms, with electromagnetic fields, these clocks exploit quantum entanglement and quantum gates to isolate and measure an atom's oscillation with astonishing accuracy. Quantum logic allows one ion to serve as the clock, while another ion is used to cool and control it without disturbing its internal state. This architecture has achieved timekeeping accuracies even finer than those of optical lattice clocks, pushing the limits of what we can observe and define in time. The implications of such precision are enormous. One immediate consequence is the ability to detect gravitational differences at extremely small spatial scales. According to Einstein's general theory of relativity, time passes more slowly in stronger gravitational fields. With optical clocks capable of detecting variations in elevation of just a few centimeters, researchers can effectively see the gravitational potential across Earth's surface. This makes it possible to use clocks as tools for geodesy, the science of measuring Earth's shape, gravity field, and sea level. Applications could include monitoring sea level rise, groundwater depletion, volcanic activity, and tectonic shifts with unprecedented resolution. In space exploration, ultra-precise clocks may enable new forms of deep space navigation. Current systems like GPS depend on Earth-based atomic clocks. Future missions could be equipped with onboard optical or quantum clocks, allowing spacecraft to navigate autonomously by comparing onboard time with signals from pulsars or other natural cosmic beacons. This would mark a significant leap in interplanetary and eventually interstellar travel capabilities. Moreover, the advent of quantum clocks challenges our fundamental assumptions about time as a uniform and continuous entity. As these instruments probe the flow of time at smaller and smaller intervals, questions arise about whether time is truly continuous or composed of discrete ticks at the Planck scale, the smallest meaningful unit of time, around 10 seconds. Though current technology is still far from reaching this scale, the development of clocks with accuracy approaching this boundary could force physicists to reconsider long-held views about the nature of time. At the intersection of quantum physics and cosmology, ultra-precise timekeeping may also help unravel the mystery of time asymmetry, why time appears to flow in only one direction. While most physical laws are time-symmetric, they work the same whether time runs forward or backward. The observable universe clearly exhibits a temporal arrow. We remember the past, not the future. Entropy increases, not decreases. Enhanced experimental tools might one day reveal whether this arrow arises from boundary conditions, quantum decoherence, or some yet unknown temporal property embedded in the fabric of spacetime. Timekeeping is also moving into the realm of quantum networks. As quantum communication and quantum computing become more viable, synchronization between quantum systems becomes critical. Conventional timing methods may not suffice in a quantum internet. Entangled particles and quantum timing protocols are being explored to coordinate operations across distributed quantum computers or secure communication links. In such contexts, the concept of time may become more relational and context-dependent, tied to the information flow and quantum correlations between systems rather than to an external, universal clock. Looking even further ahead, speculative theories in physics entertain the idea of manipulating time itself. While current science rules out time travel in the Hollywood sense, general relativity allows for theoretical constructs such as closed time-like curves, loops in space-time that could allow an object to return to its past. Wormholes, if they exist and can be stabilized, might also permit shortcuts through space-time. So far, these remain in the realm of theory, requiring exotic matter and energy configurations not observed in nature. Yet, as timekeeping becomes ever more refined, the boundary between what is measurable and what is imaginable continues to shift. The convergence of advanced timekeeping, quantum mechanics, and theoretical physics even raises philosophical questions. If we develop a clock so accurate it can detect minuscule fluctuations in spacetime itself, are we still measuring time in the traditional sense, or probing the quantum structure of reality? Could time eventually become an emergent property, not a fundamental one, something that arises from the interactions of more basic entities in the universe? Some physicists propose that time, like temperature, is not fundamental but statistical, a large-scale effect of microscopic states. Experiments enabled by future clocks may someday test these bold ideas. From a practical perspective, we are also approaching a transition in how time is distributed and accessed. As 5G and emerging 6G networks demand ever faster data transmission, nanosecond-level synchronization between devices becomes crucial. Time as a utility, delivered over fiber optic cables or satellite links, may soon rival electricity and internet connectivity in importance. Some countries are already investing in national timing infrastructures that operate independently of GPS to ensure resilience against cyber attacks or space-based disruptions. In conclusion, the future of time is far from static. Just as sundials gave way to gears and gears to atoms, so too will atoms give way to quantum phenomena and beyond. Timekeeping is evolving from a method of coordination and measurement into a means of exploration of Earth, the cosmos, and the deepest structures of physical reality. As we step into this new era, our understanding of time will not only become more precise, but may be fundamentally transformed. Time has always been central to our science, our technologies, and our sense of existence. In the quantum future, it may become the key to understanding everything. Time is among the most familiar yet most enigmatic concepts in human experience. We live by it, measure it, remember it, and fear its passing. It structures our days, our memories, and even our sense of self. And yet, for all its importance, time remains one of the least understood elements of our reality. Over the course of human history, our scientific understanding of time has evolved dramatically, from ancient sundials tracking the shadow of the sun to quantum clocks measuring atomic oscillations with nearly unimaginable precision. And still, we find ourselves asking the most fundamental questions. What is time, really? Where did it come from? And does it have an end? The journey of time measurement is not just a tale of technological progress, but of changing worldviews. In ancient civilizations, time was cyclic, rooted in the rhythms of nature, the sun rising and setting, the moon waxing and waning, the seasons returning. Calendars were religious tools, and time was something humans lived within, not something they could control. With the advent of mechanical clocks, time began to be seen as something external, something that could be measured, divided, and synchronized across space. It became a tool of power, productivity, and precision. Science has transformed time from an experiential dimension to a subject of empirical investigation. It has given us definitions and equations, standards and measurements. We now define the second not by celestial motion, but by the vibration of a single atom. We've discovered that time is not the same everywhere in the universe. It stretches and compresses depending on speed and gravity. A clock on a satellite ticks differently from a clock on Earth's surface. Time, once thought to be universal and immutable, is now understood to be dynamic, a quantity shaped by the forces and conditions of the cosmos. And yet, for all our measurements and models, time remains mysterious. In physics, it is a parameter in equations, a way to describe change. But why does it seem to flow in one direction? Why do we remember the past, but not the future? Why do we experience a now? These are not just philosophical questions, but deeply physical ones. The laws of physics are largely time-symmetric. They do not distinguish between past and future. The arrow of time, the fact that we perceive it as moving forward, is tied to entropy and the second law of thermodynamics. But why the universe began in a low-entropy state is still an open question. We do not know whether time has a beginning or an end, whether it is continuous or discrete, or even whether it is fundamental or emergent. Cosmology adds further complications. According to general relativity, time began at the Big Bang. There was no before in the way we understand it. Yet theories of quantum gravity suggest that time may dissolve at the Planck scale, or that it may be a byproduct of more basic physical processes. Some models propose that the universe undergoes endless cycles of expansion and contraction, making time potentially infinite. Others suggest that time might be an illusion, a construct of human consciousness, or a byproduct of information processing in the brain. In quantum mechanics, time plays a puzzling role. The equations governing particles and waves treat time as a fixed background, even while everything else is uncertain and probabilistic. Unlike position or momentum, time has no operator in quantum theory. It is not something we measure in the same way. This creates tension when trying to unify quantum mechanics with general relativity, where time is woven into the geometry of space-time. The quest for a theory of quantum gravity, a framework that unites the large-scale and small-scale understandings of time, is still ongoing, and with it, the hope of answering some of these deepest questions. Biology and psychology offer yet another dimension to the mystery. Humans do not perceive time linearly or uniformly. Time seems to slow down during moments of danger, speed up with age, or stretch and compress based on attention and emotion. These subjective experiences do not contradict physics, but show that time is not just something that exists out there in the universe. It is also something constructed in the brain. Neuroscience is beginning to reveal how the brain keeps time through circadian rhythms, neural oscillations, and cognitive processes that encode memory and anticipation. Time is not just measured by clocks. It is felt, lived, and remembered. In the modern world, time has become more than just a philosophical or scientific concept. It is infrastructure. It enables global communication, powers GPS navigation, coordinates international finance, and synchronizes millions of digital systems. We have built a civilization that depends on precise, shared time. And as technology pushes forward, the demands on our timekeeping grow ever more intense. Quantum networks, autonomous vehicles, financial microtrading, and deep space exploration all require synchronization down to the nanosecond or better. Time is now an engineered resource, delivered like electricity or data. Yet in this march toward ever more precise control, we must not lose sight of the deeper questions. Science can tell us how time behaves, how to measure it, how to synchronize it, but it still cannot fully explain why time exists or what gives rise to our experience of it. We know that time slows down near a black hole, and we can measure the dilation. But what does it mean to say that less time passes for someone? What is the essence of the present moment, and why does it feel different from the past or future? In this way, time is a frontier, not just of physics, but of understanding. Like space, energy, and matter, it is one of the basic building blocks of reality. Yet it is the one most intimately tied to our awareness, to our history, to our fate. We are beings embedded in time, carried along by its current. Whether it is an illusion, a process, a dimension, or something else entirely, time remains the stage upon which all experience unfolds. The scientific journey through sundials, gears, atoms, and quantum oscillators has taught us much, but it has also revealed the depth of what we still do not know. Time is more than what clocks measure. It is the pulse of the universe, the rhythm of life, the mystery at the heart of existence. And so, even as we master its measurement, we continue to wonder, what is time? Where is it taking us? And what will we find at its end? Good night.